Hey there, Geometry. Thanks for tuning in for another episode of Math with Mullins. Today we're going to be looking at lesson 3.4, proofs with perpendicular lines. So our main goals are these three things. Find the distance from a point to a line, so that's going to be using the distance formula. Prove theorems about perpendicular lines, maybe even look at a few newer theorems, just so we know what we can do and how we can put them in proofs, and then how to solve real life problems involving perpendicular lines. The first thing we're going to talk about is the distance from a point to a line. So this is the very first thing we have in our notes today. That's the length of the perpendicular segment from the point to the line. So maybe from like point A to point B, how long is that line? This perpendicular segment is the shortest distance between the point and the line. Remember, we still are going to be seeing the distance formula, which is x2 minus x1 squared plus y2 minus y1 squared. Okay, that might be important to copy in your notes. So if you don't have the distance formula there in your notes yet, go ahead and copy that down. And when you're ready, let's click play to see how it's done. All right, so what we're going to do is we're going to find the point from A, which is here, to line BD. And that line intersects right here at this point, which is using point C. Okay, so we can say maybe this is x1, y1, and this is x2, y2. Okay, so remember, we're still going to use that distance formula. We're going to subtract our x's and square them, subtract our y's and square them, and then find the distance of that. So I'm going to do x2 minus x1, that's 1 minus negative 3 squared, plus y2 minus y1, that is negative 1 minus 3 squared. Okay, 1 minus negative 3 means 1 plus 3, that's 4, and 4 squared is 16. And then 1 minus 3, that's negative 4 squared, that'll be 16 again. So we're trying to find the square root of 32, and that's probably going to give us something around 5. So if we type that in our calculator, we're going to get about, let's see, rounding it maybe to 5.6 or 5.7, 32 square root. Yeah, we can say 5 point, around 5.7. That'll work for us, okay? So here's the next one. Maybe see if you can pause the video here, try it on your own, and when you're ready to check it, click play. So here's point E, and we're going to line FH, which is here at point G. I'm going to say this is x1, y1, and these are x2, y2. So I'm going to do the square root of 1 minus negative 4 squared plus 2 minus negative 3 squared. Okay, that makes it a little bit easier for us. 1 minus negative 4 is 5, and 5 squared is 25. 2 minus negative 3 squared is also 5, and another 5 squared is 25. So I'm trying to find the square root of 50. So if I take the square root of 50 on my calculator, I'm getting about 7.1 as my final answer. The next thing we're going to talk about are 3 different theorems, and we are going to fill in some fill in the blanks here. So you see a picture of line G and line H, and they're making 2 right angles. So if the 2 lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. So if angle 1 is equal to angle 2, then G is perpendicular to H. That's what you need to write in your notes. The picture should already be there in your notes as well. For theorem 3.11, the perpendicular transversal theorem, pretty much the same thing. Now we're just adding another set of parallel lines. In a plane, if a transversal is perpendicular to one of 2 parallel lines, then it is perpendicular to the other line. So again, copying this down in our notes, if H is parallel to K and J is perpendicular to H, then J is perpendicular to K. So again, here is H and K, those are parallel. If J is already perpendicular to H, then J can also be perpendicular to K. Okay, and then theorem 3.12, the lines perpendicular to a transversal theorem. That just means in a plane, if 2 lines are perpendicular to the same line, so we have line P, and then M and N are both perpendicular, then they are parallel to one another. So if M is perpendicular to P, and if N is perpendicular to P, then M has to be parallel to N. Go ahead and make sure you have those 3 lines written down, and then we're going to go on and talk about how could we maybe use this in a proof. So use the diagram to prove the perpendicular transversal theorem. And that perpendicular transversal theorem, remember, is if you have two lines that are parallel and one of them is perpendicular, then they should all be perpendicular. Okay, so maybe the first thing we want to start with is drawing our statements and reasons. And we'll go through this one together. So it's not necessarily, again, having to remember all the daunting tasks of all the proofs, but how can they all be connected? So if H is parallel to K and J is perpendicular to H, that was our given. Okay, then we can go forward and maybe say the measure of angle 2 is equal to 90 degrees, and that's the definition of perpendicular lines. Okay. We also know that angle 2 is equal to angle 6, because that's the corresponding angles theorem. Okay. And knowing that, then we can maybe say that angle 6 is equal to 90 degrees, and that would just be using either substitution or the transitive property. So our site subs/transitive property. So that now if angle 6 is 90 degrees and it's matching angle 2, remember the perpendicular transversal theorem, if we go back to it, and it says if it's perpendicular to one or two lines, then it is also perpendicular to the other line. We know that they're going to be perpendicular because 2 and 6 are matching. So now we can say that J is perpendicular to K using the definition of perpendicular lines. Okay. This photo shows the layout of a neighborhood. Determine which lines, if any, must be parallel to the diagram and explain your reasoning. So here is, I don't know if you can see this on your paper, but this is line S, T, U, and then P and Q. And from the looks of it, it looks like there are a few that are parallel. S and T appear to be parallel because they have a 90-degree angle. And again, I don't know if that's easier to see in your paper. Okay, but that just is showing where those 90-degree angles are. So let's start with maybe just P and Q. P and Q are both perpendicular to line S because they're showing that 90-degree angle. So that could be one reason. So since P and Q are both perpendicular to line S, so when we talk about the perpendicular lines to a transversal, the P could be parallel to Q. So P is parallel to Q using lines perpendicular to a transversal. Okay, so then if you keep looking, S and T also look like they could be parallel because they are notated with that right angle. So S and T are perpendicular to line Q because it's intersecting that right angle at line Q by the same theorem. So S is parallel to T. Okay. And then I think this is our last example in our notes. Use the lines marked in the photo. Is B parallel to A? Explain your reasoning. So if you look closely, we have some right angles notated here, okay? And because we see those right angles, we can say that yes, both are perpendicular to line C, or line C, maybe not line C, but they're both perpendicular to line D because they're both showing that on line D right here. So we use the perpendicular lines to a transversal theorem. Okay. Then our last one is B perpendicular to C. If you look at B and you look at C, technically we can say B is perpendicular to C because of the corresponding angles theorem. If this would be 90 degrees, then this one should also match using those supplementary angles or the knowledge of those supplementary angles. So we can say, yes, B is perpendicular to D, and C is also parallel to D. So we use the perpendicular transversal theorem. Okay, that would just be another way that you can see it. So since B is perpendicular to D, you can assume that. I just took, you can also take A is perpendicular to C by that right angle. That is all we had for today. Thanks so much for tuning in, and we'll catch you next time.